All right, last recording of the semester. Oh, can't minimize it. Sorry, screen. So we've got day 3 of the finals review packet today. Again, my disclaimer that this is just for review purposes, right? If you want to know what's on the test, go to the outline, post it on the course webpage. All right, so let's talk about number 1. Explain why the boiling point of F2 is negative 188.14 degrees Celsius, whilst the boiling point of HF is 19.5. Both of those are gases at room temperature, right? Because we're at about 24 degrees in here. So let's look at them. It's got to be something related to structure, right? What's the structure of F2? There's a Lewis structure for F2 versus HF. Right, boiling point of negative 188 versus 19.5. Very significant difference here. What causes this? What causes boiling point anyway? Period. Intermolecular forces, right? Driving factor. Of course, we're assuming that we're at atmospheric pressure and we're not at some extreme temperature. And we're not at some extreme pressure, right? Not the top of a mountain. So we're assuming we're at room temperature, right? Normal atmospheric pressure. IMFs are the driving force, right? Intermolecular forces. Let's review what those are. Particles in the liquid phase are close together, right? They feel forces of attraction to each other, which we call IMFs. And remember, I emphasized this big time when we talked about intermolecular forces. I said, if you talk about bonds breaking when a gas particle, when a particle in the liquid phase vaporizes to the gas, if you say bonds break, is that correct or incorrect? That's incorrect, right? Because if bonds break, would that be a physical change? No, that'd be a chemical change, right? If you broke this bond when you vaporized it, it would no longer be HF, right? And vaporization is a physical change, not a chemical change. So I warned you many, 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 many times, and still people wrote it on the test, by the way, that when you vaporize a liquid, bonds break. That's not true, right? When you vaporize a liquid, bonds do not break. What do? You overcome IMFs. Good job. You can think about intermolecular forces as like, you know, the chains that are holding you down in the liquid phase, right? And you've got to have enough energy to overcome those forces of attraction between molecules. So intermolecular forces are driving the boat here. So let's just compare then the intermolecular forces in these two molecules. What IMFs would F2 have? First, let's ask ourselves, is it polar? Is it a polar molecule? Polar or nonpolar? Nonpolar, right? Even though fluorine is extremely polar, extremely electronegative, can you share electrons unevenly with yourself? No, that doesn't make sense. So what IMFs would this have? London forces only, right? London dispersion only. And is that a big molecule? Are we talking about a 30 carbon chain here or a 50 carbon chain? No, this is a very small molecule. So are those going to be strong or weak? They're going to be weak, right? Because that's a small molecule. What about in HF? Is that a polar or non-polar molecule? This one's polar, right? It's going to have a pretty significant dipole moment, right? The dipole moment is going to be facing this way, with this being the partial positive and this being the partial negative, right? And what kind of IMFs would we have here? We have hydrogen what? Hydrogen bonding. Now, is that an actual chemical bond? It's not a chemical bond, right? What is it? It's a very special, strong dipole-dipole force. We also have London as well. Everything's got London, right? But this is the big influence, right? Hydrogen bonding, that's a strong IMF. Whereas this is going to be relatively weak. So this is what makes the big difference here, right? Very polar, very strong hydrogen bonding, very strong forces of attraction that have to be overcome to boil this. Questions on number 1? Questions on 1? All right. Let's do number 2. Move the screen up a little bit. All right, which of the following will have a higher vapor pressure? Let's remind ourselves what vapor pressure is. If I've got a liquid in a sealed container, right, here's my liquid. Is it just liquid in there? Is it only liquid? Or is some of that liquid vaporizing? Some of that liquid's vaporizing, right? And that vapor creates pressure. So we have to ask ourselves, okay, what's the relationship between intermolecular forces and IMFs? If you have strong IMFs, what would that mean in terms of vapor pressure? If the particles in this liquid are being held together by strong intermolecular forces, would you expect there to be a lot of vapor pressure or not a lot of vapor pressure? No, not a lot, right? So it would be a low vapor pressure. Which is why you have to add a ton of energy to make the vapor pressure equal the atmospheric pressure. What happens at that point when vapor pressure equals atmospheric pressure? We call that the boiling point, right? So this all comes back to boiling point, IMFs, they all go together, right? If you've got strong intermolecular forces, you have a low vapor pressure, which means you have to add a ton of energy to get the vapor pressure to equal atmospheric pressure for the thing to boil, right? So it's just an extension of the previous problem. So we want the one with the highest vapor pressure. So are we looking for the one with the strongest IMFs or the weakest IMFs? We're picking the one with the weakest IMFs, right? Because if you've got weak IMFs, right, then this vaporizes really easily, which means you'd have a high vapor pressure. So now we just got to go through each one of these molecules and assign IMFs, figure out what we can do. So let's start with the first one. What IMFs will this have? London dispersion, right? Anything else? There's another one. What's the other one? What? Hydrogen bonding, right. Where is it? Right, it's on this piece right here. All right, let's go to the next molecule. What IMFs will this one have? What's the one you list for everything? London dispersion. You can call it London. You can call it London dispersion. You can just call it straight up dispersion. I'll accept any of the above. Are there any others? There's another one. What is it? What? Hydrogen bonding, right. Where's that? On the OH, right here. What functional group is that? That's alcohol, good. What functional group is this? Amine, good. Okay, let's do this one. It's obviously got London dispersion. Anything else? The answer is yes. There is something else. What is it? What? The carbonyl, yep. Specifically, this functional group is called a what? That's ketone. And what IMF is it capable of? Starts with a D. Dipole-dipole, right. Why? Because this is partial positive, this is partial negative right there. So that's dipole-dipole. And then lastly, London dispersion, of course. Anything else? There's hydrogen bonding and dipole-dipole, right? What's this functional group called? Because this is a functional group that you're responsible for. What's this one? Carboxylic acid, right? So the hydrogen bonding is from right here, and the dipole-dipole is from right here, right? And that's a ketone, that's an alcohol, and that's an amine. Just a nice review of our functional groups while we're at it. So of these four, which one has the weakest IMFs? Which one? Right, so this one, the one with the ketone. You don't know how to name it yet, that's okay. You'll learn how to name it in organic. This one is our winner, right? That one's going to have the highest vapor pressure because it has the weakest intermolecular forces. Questions on how we diagnose this one? Okay. Intermolecular forces tend to be kind of a rear end kicker. So I try to put several on here. Because, hey, here's another one. What's viscosity? Resistance to flow, right? Resistance to flow. Right, if you take a liquid and you pour it, it's just, right? It's got a high viscosity. And so what would the relationship be between IMFs and viscosity? Right, increased IMFs is increased viscosity. Good. Because, why? If they have strong forces of attraction in between the particles in that liquid, they're not going to flow really easily. Doesn't make that sound effect, but you can think about it that way. Questions on 3. That was a quick explanation in light of the previous 2. All right. Let's do this one. Number 4. When magnesium metal reacts to hydrochloric acid, hydrogen gas and magnesium chloride are produced. Is this a redox reaction? So first we have to write the equation. What's the formula for magnesium metal? Is it Mg plus 2 or just regular Mg? Regular Mg, right? Because metal tells you, look at the periodic table. So magnesium solid. Hydrochloric acid would be aqueous, it's a solution. We're producing hydrogen gas. What's the formula for hydrogen gas? H2, right? As a gas, that's diatomic. H2 gas. Plus, what's the formula for magnesium chloride? Mg what? Cl2, and that would be aqueous. Is this balanced? What do we need to do to balance this? 2 HCl, right? Now we just ask ourselves, is it redox? So what do we have to do to determine if it's redox? We have to figure out the oxidation numbers, right? What's the oxidation number for magnesium metal? 0, it's pure element, most stable form. What's the oxidation number for hydrogen in a compound? +1, so that means chloride here is -1. What's the oxidation number for hydrogen gas? 0. Magnesium is a group 2, so what's its oxidation number? +2, so what does that mean? Chlorine is here, -1. Do we have anything that's not changing? We have a spectator, right? The chlorine isn't changing, so we can just kind of ignore it if you want. Might simplify things a little. So now we're comparing before to after. Let's review, right? Leo and Ger, right? Lose electrons is oxidation, gain electrons is reduction. So magnesium goes from 0 to +2. Is that a loss or a gain? That's the loss of electrons, right? That's the LEO. And then hydrogen goes from +1 to 0. Is that a loss or a gain? That's a gain, right? Is it possible to have 2 GERs or 2 LEOs? It's not, right? So if you come up with that, you need to go back and check your oxidation numbers or check your formulas. So is this redox? The answer is yes. What is the oxidizing agent? Oxidizing agent? Remember, agent means allows to occur. So the oxidizing agent is the thing that actually gets reduced, right? So it would be the hydrogen in HCl. And what would the reducing agent be? That would be the magnesium. Okay, remember, agent means allows to occur. So if you are the reducing agent, that means you are getting oxidized because they are opposite each other. Questions on 4. Okay. Oh, look, it's another solution stoichiometry problem. All right, let's do this one. Lithium sulfate has what formula? Li2SO4, and it's aqueous. I told you it's solution with a molarity of 5 molar and 0.07689 liters. It's combined with barium chloride, and it's got a molarity of 6. It's a pretty high molarity. And 0.08146 liters. All right, I told you the precipitate contains barium. That was really nice of me. I'd probably just write on the test what mass of the precipitate and let you figure out which one it is, right? Because that's more likely to be what you would get. I wouldn't tell you that it contains barium. I'd just say what mass the precipitate's formed. All right, so we know our precipitate contains barium because I told you. What's its formula? BaSO4. And what's our other product? LiCl. And that would be aqueous. Need a coefficient of 2. Okay, so we want to know what mass here in grams am I going to get of this precipitate. Is this regular stoichiometry or is it a limiting reagent type problem? Limiting reagent. All right, so we've got to do the calculations twice. So are we okay if I do it all as one, or do we need to break it up? All right, let's do it all as one then. So for lithium sulfate, 0.07689 liters times 5 moles Li2SO4 per liter, so that gets rid of liters. Now it's time for mole ratio, which is 1 to 1. 1 mole Li2SO4 for every 1 mole BaSO4. So moles of lithium sulfate go away. Now we just need to calculate the molar mass of barium sulfate. So 137.327, 32.066. You get 233.39 for your molar mass. Do we agree? All right, so times 5 times 0.07689. 89, keeping 3 sig figs, 89.7 grams. We've got to do it again because we don't know who the limiting reagent is. We've got to do it again. So volume in liters, 6 molar Meters cancel. Still 1 to 1. Moles cancel. Don't have to calculate that molar mass again. Once you calculated it once, that's good enough. Moles cancels. So 0.08146 times 6 times 233.39. Keeping 3 sig figs would give me 114 grams. So which is my answer? Right. This would be my theoretical yield. Do we agree on 5? Yes. All right. Number 6. Oh, didn't do a very good job erasing. Yeah. A sample of solid potassium chlorate is heated in a test tube and it decomposes into solid potassium chloride and oxygen gas. 650 milliliters of oxygen gas was collected over water, 22 degrees Celsius, total pressure 754 torr. Vapor pressure of the water is 21 torr. What was the original mass of the potassium chloride sample? We got a lot going on here, right? So we're taking our sample, and there's our solid, right? We're heating it. There's our Bunsen burner, and then we've got some sort of tubing here to collect the gas, right? And then we're bubbling it into water. So here's some water. And it bubbles up through the water. There we go. All right, so you wouldn't have to draw that out, but just so you get an idea of what we're doing here, right? So we've got our sample. What's the formula of potassium chlorate? It's K what? ClO3, right, solid. And we're heating it. So that's how we represent that we heat it. It's decomposing into potassium chloride, so what's that? KCl. And oxygen gas has what formula? O2. Is this balanced? What do we need to do to balance it? 2, 2, 3. Let's see. 6 oxygen, 6 oxygen, 2 potassium, 2 potassium, 2 chlorine, 2 chlorine. I agree. Okay, so we are interested in the gas. It's 650 milliliters. And it's at a temperature of 22 degrees Celsius. And P total is 754 torr. And P of the water is 21 torr. And I want to know what was the mass of my sample. So how can I do this? What's the only way to do this? There's only one explanation for this. You have to use the ideal gas law, right? Which is PV equals nRT. Now remember, the equations will be on your reference page. You just need to know which one to use, when, and how to use it. So we go through our list of variables. Is our pressure in the appropriate unit? No, it's not. What does our, first of all, we need to do something. How do I get the pressure of the O2? Subtract, right? So what would that be in torr? 733. Do we agree? Yes? Is torr an appropriate unit? No. What do I have to do? And how do I convert? That conversion factor will be on the exam, on the reference page. How many torr are in 1 atmosphere? Does anyone remember? 760, right. So, 733 divided by 760, 0.964. Let's just carry out an extra decimal place. 5. We'll round at the end. Okay, can I keep Celsius as my temperature? What do I have to do? Add 273, right? So that's 295 Kelvin. And can I keep milliliters as my volume? Convert to liters. So what is that in liters? Right, 0.650 liters. Now I'm ready to go, right? So I'm solving for what variable? N, right? Because I'm going to do some stoichiometry. So if PV is equal to nRT, N is equal to what? PV over RT. Or you could have plugged directly in and solved just like you did in algebra class. Work out the same either way. So my pressure, 0.9645. My volume, 0.650. What's R? Is it 8.314? That's not the version we're using. What are we using? 0.08206, right? I'm leaving my units off here because I'm lazy and I'm running out of space. My temperature is 295. So 0.9645 times 0.65 divided by 0.08206 times 295. I got 0.0259 moles. It's 2589775. Is that what you got? Is that a reasonable number of moles? Yeah, that's a reasonable number. If you came out with like 2,000 moles, is that reasonable? No. That's a reasonable number of moles. Now what do I do? Now that I know moles, I have to do what? Oh, you got to do some stoichiometry. So I'm going to work the rest of my problem over here. 0.0259 moles O2. There are 3 moles O2 for every 2 moles KClO3. Run out of room again. Molar mass of potassium chlorate. That's potassium, 39.09. 122.55. Okay, so now we can get a final answer. So 0.0259 times 2 times 122.55 divided by 3. Original mass rounded to, how many sig figs am I keeping? What's my least number? 2, right. So my calculator spits out 2.116, which I round to 2.1 grams. Do we agree? So this is first it's a gas laws problem, then it's a stoichiometry problem second. Questions on 6. Okay. Draw a heating curve to represent the enthalpy change that occurs when 25 grams of ice is heated to 25 grams of water, liquid, 26. Calculate change in enthalpy. All right, so we're gonna do some phase change in here. All right, we're initially, this is time, this is temp. All right, we're initially at 0. We're going to start heating. What's going to happen over time to that ice? It doesn't initially start changing temperature, does it? What happens first? It has to, what happens? You have to melt it, right? So for some period of time, the temperature doesn't change because all that energy is going into melting. So that's calculation number 1. Now we can start increasing the temperature. So if our final temp's 26, is that anywhere near the boiling point? No. So you don't have to worry about dealing with that process of vaporization. We're just increasing the temperature. All right, so this is just a 2 calculation problem. Do we agree? All right, so for the first calculation, this is for melting, right? Q is equal to what? That's this one, that's number 2. N times delta H of fusion or vaporization? Fusion. So this is 25 grams. So we've got to convert grams to moles, right? So grams cancels. What's the heat of fusion? It's 6.01? It's on the reference page. Let's look at it. I think it's 6.01. I want to get all my sig figs right. There's our reference page. That's heat of, yep, 6.01. Yay, Dr. Rock. 6.01. And that's in kilojoules per mole. So we do some multiplying and dividing. 25 times 6.01 divided by 18. Now this is going to give me an answer in kilojoules, right? So this is 8.3. Let's carry out extra decimal places. 47 kilojoules. Be careful though, because is this calculation going to be in joules when, kilojoules when I spits out? No, it's going to be in joules, right? So number 2 is there's your Q equals MC delta T, right? And we're using the heat capacity of liquid water because now it's in the liquid phase. And we don't have to convert to moles, right? So that's 25 grams times 4.184 joules per gram degrees Celsius times, what's delta T? Is it 0 minus 26 or 26 minus 0? 26 minus 0, right? It's always final minus initial. Times 26 degrees Celsius. Degrees Celsius cancels, grams cancels. Gives me an answer in joules, okay? Make sure that you do some sort of conversion before you add those. So 25 times 4.184 times 26 gives me an answer in joules, 2,719.6 joules. How could I convert that to kilojoules? All right, we just move the decimal 3 to the left. So 2.7196 kilojoules. Now we're in the same unit. Now we can add, right? So Q total is just the sum of those. So plus 8.347. So that would be 11. How many sig figs are we keeping? Well, I guess technically we keep 1. Let's just pretend there's a 0.0 there. So I can have 2 sig figs. 11 grams. Oh, not grams. Kilojoules. Do we agree? All right. All right, complete the table. Now, if you're looking at the reference page, I do give you the geometries. okay? Just like on exam 1, which this was from, I'm not going to make you memorize the geometries as long as you can apply it, okay? And that's what I'm looking for you to be able to do, all right? So just so you know. All right, the formula is nitrate. What do we need in order to draw the Lewis structure? How many valence electrons, right? Nitrogen has how many? 5. And oxygen has how many? How many? Oxygen has how many? 6, right? And then what do we do for that negative charge? Plus 1. Right, so that's 5 plus 18 plus 1. So that gives us 24. Who goes in the middle, nitrogen or oxygen? Nitrogen. Why? It's not so that it can be symmetric. That's not the correct answer. Least electronegative. Good. So N goes in the middle. And then we're going to connect everybody with single bonds. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, is that my final answer? What do I need to do? What's wrong? Okay, well, we do need brackets, but there's also something more fundamentally wrong, too. It needs a double bond, right? Because nitrogen doesn't have an octet. Is there resonance? Yes, there's resonance because I could have the double bond here or the double bond here, right? So I wouldn't ask it unless I specify. You don't have to draw them all. But just so you know, right? That would have worked. Now, I didn't say draw all resonance structures. If you go through and do your formal charges, is one of these favored over the others? Is one of those going to be favored over the others in terms of formal charge? No, it's not. It's equally probable. All right, so now we do electron domain geometry. What do we look at to determine that? The central atom? Yes. And what we're looking at is the number of things. I used a real technical word there. How many things are on the central atom? First of all, does a double bond count as one thing or two things? It counts as one, right? I use the example, you have twins, it counts as one pregnancy. You're not having 2 pregnancies, you're having 1, right? I mean, technically you're pregnant with 2 people, it's 1 pregnancy, right? That's how you can think of it. So 1, 2, 3, 3 things on the central atom. So you may have them memorized because you've done it enough times. If you haven't, that's okay. Electron domain geometry would be trigonal planar. And then let's go back to our Lewis structure. Are there any lone pairs on the central atom? No. So what does that mean the molecular geometry is going to be? Trigonal planar as well. What does planar mean? Flat. Right, so this is a flat molecule. And then is there resonance? Yes, we just drew it down there. Do we agree on number 1? All right. Let's go on to the next one. How many valence electrons does sulfur have? 6. And how many does fluorine have? 7. So that's 35. What do I do for that charge? Add 1. So that gives me a total of 42. Who goes in the middle? Sulfur. Right. 1, 2, 3, 4, 5. Let's do 4, 6, 8, 10. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. What do I do now? Where do they go? On the central atom. Am I done? What do I need? You need those brackets to show the charge. All right, now let's look at the sulfur. How many things are on the sulfur? 6. So if we look at our reference page, what electron domain geometry is that? That would be octahedral. Octahedral. But now we have to ask ourselves, is there a lone pair on the central atom? Yes, that changes the molecular geometry, doesn't it? Because that lone pair is going to occupy space. So what molecular geometry is that? Square pyramidal, right? That lone pair is going to occupy space down here. So that gives us square pyramidal. Is there a resonance here? No, there's not. All right, let's slide everything up. All right, let's do PCl3. Phosphorus trichloride. How many does phosphorus have? 5. And how many does chlorine have? 7. So 5 plus 21 would give me 26. Okay, who goes in the middle here? Phosphorus, right? Least electronegative. So P in the middle, Cl, Cl, Cl. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Where do those extra ones go? On the central atom, 26. Do I need to make any double bonds to give any octets or anything like that? Okay, so let's look at our reference page. 4 things on the central atom, right? So what does that correspond to? Tetrahedral. And while we're here, we've got the Lewis structure handy. We can look at it. What molecular geometry would that be? Trigonal pyramidal, right? Because that lone pair will take up space. So tetrahedral. And trigonal pyramidal. Is there resonance? No. All right, last one, ClF4+. All right, so chlorine's got 7, right? Chlorine's got 7. So 5 times 7 is 35. What do I do for that plus? Right, you gotta subtract 1. Make it 34. Is it normal? Does it happen really frequently to have an odd number of electrons? No, that's not something that happens really frequently, right? Because that's very unstable. That's a free radical. Okay, who's in the middle, chlorine or fluorine? Chlorine. So ClF4. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. What do I do? 34. And then what else do I need? Brackets. Is it okay to, instead of make that lone pair sit on the central atom, what if I just turn it into a double bond? Would that be okay? Am I allowed to do that? No, you're not, right? You're only allowed to make double bonds to either fix a formal charge problem or give a central atom an octet. So no, you can't make it into a double bond unless there's good reason for doing it. Okay, central atom's got 1, 2, 3, 4, 5 things on it. So looking at our handout, that corresponds to trigonal bipyramidal. And is there a lone pair that we have to look at? Yes, that lone pair will take up space. So one lone pair would give us seesaw. No. Questions on the last problem of the review packet? All right, the next time I will see you, unless you come see me in office hours, will be for the final exam. So have a great weekend and happy studying, and I'll see you next time.